I want to say thanks to the organizer for letting me come here and speak. So today I'll be talking about a result that I still up in archive. And the idea is to start first by explaining what the Schreier's formula is, and that is a theorem due to wrong spelling. Oh, no. Nielsen and Schreier. That states that any subgroup of a free group is itself a free group. And in particular, if you know the number of generators of F, so say n, and then you also know that the index is finite, then you can compute the generators of H by the following formula. So H is going to be isomorphic to Fk, and minus 1 is equal to F inverse K minus 1. Okay, so the idea is to move this result in the level of von Neumann algebras. We have something for the index coming from von Jones, and then the thing that will be able to graph this n is going to be these free entropy dimension quantities. So the one that we're going to work with is the 5-pointed star, which I'm going to draw as Voiculescu did. That's this thing. So the idea is that, so this is the entropy that we're going to be working with. So the idea is that given a finite index of inclusions, so n subset of M, and the generating set X of n, there exists a generating set Y of M such that the following formula holds. So okay, so that's the hope for us here. The idea here is we're going to restrict ourselves to a particular case when we look at cross products. So that's what we're going to be doing. And in particular, towards proving a result like this, Shlyakhtenko was able to show for, given, so in 2003, given a trace preserving outer action G on this is of a finite abelian group on a tracial von Neumann algebra factor here, one has the following estimate. So there exists a generating set Y of the cross product. Oh, I should call this something alpha here. And the generating set X of M, and that gives us the following formula.
Wait, I'm confused here. Okay. Given this, you can find this generating set X, or is the X part of your assumptions?
Oh, Oh, sorry, 1 second. I also need something else. Sorry, this is bad. So, and then epsilon greater than 0. No, the whole point is that you have a generating set for M and a generating set for the cross product. So there exists one. You'll construct it. I don't like writing it here. It's going to be too small.
Did I ask what you meant by finite index of inclusions?
Yeah, it means that because you have a Joan index here, I just mean that this number is finite when I'm looking at the von Neumann algebras.
Inclusion of finite.
An inclusion of.
So like there's 6.
Yeah.
Since,
Inclusion. Sorry? Oh. Okay, so the equation that we end up getting is the following one. Inequality that we end up getting is the following one. So y minus 1 is less than or equal to the order of the group, delta plus epsilon. So the idea here is just that you have a generating set, but you don't get equality. In here, the index, because of the cross product, is just going to be the order of the group. And so the goal here is to use other quantities in free probability to be able to compute something like this. So our setting is going to be the following. Yeah, go ahead. This is the, it's coming from the non-microstates, so it's coming through derivations. Okay, so let G act on M, tau, alpha, be a trace-preserving action. Let G be a finite group, and M, tau, is just a tracial von Neumann algebra. Okay, so what I mean by a trace-preserving action, what I mean is you have a map from G into the automorphisms of M. So G goes to alpha x. And then this allows me to upgrade. Yeah, sorry, it's a habit. Yeah, an element in the group. Okay, so yeah, I can upgrade this into the Hilbert space. So I have yes, that's right. And it leaves the trace alone. And so because of this reason, I'm able to upgrade this at the level of the Hilbert space. So I can define a unitary such that it sends the map of x. I'm going to keep doing that. That's why you do this. And then the cross product is just going to be the von Neumann algebra generated by M and these unitaries. So an arbitrary element in the cross product is going to look like the following. So if you give me an element here, then you can rewrite this as a sum of elements in G, X, G, UG, where XG lives in M for all G and G. And then the trace that you have here is coming from just looking at what it does on the trivial element coming from the trace.
Are you like still assuming the action is outer or something? Otherwise,
No more. No, I'm just assuming that it's trace preserving. Is a trace preserving action, and
Then I don't know that you can faithfully represent it on this open space.
I mean,
I don't understand how is the cross product being represented on the standard form of M, unless you make assumptions about the action being like free or something.
Okay, so the quantities, to relate back to free probability, what we usually will work with is derivations. So our goal is going to look at the derivation space. So what this is just derivations. First of all, I need to define a few more things, sorry. So let X be a generating set of M, and let A be the polynomial algebra that we saw. These are going to be self-adjoint, so I don't need to put the star that people were putting. And so the derivation space that I'm talking about is going to be derivations on A, tau. So D from A into L2 of M up, such that D is linear and satisfies the Leibniz rule. So the Leibniz rule that I'm discussing, I'll show you here. So L2 of M tensor M op is a bimodule with respect to M. And the action is coming from that. So you have, if you have X, Y, A, and B, and M, then the action is X. Yeah. You're just acting on the left to be in the most outer ones. And so in here, what you can do is you can witness the multiplication in the following way. And so the goal now is going to give the derivation space a M tensor M bimodule structure from the right. So given a derivation tau, this is just equal. This is just going to be pointwise, and then you just act on it on the left, right? Because the X element lives in L2 of M tensor M tau. Okay, so now our goal is going to be to take a dimension of the derivation space coming from this action. So in here, what we can do is we're going to define a map, derivation tau into L2 of A. just pointwise. So D is going to go on the unit. So this is just so that we can give a Hilbert space structure to the derivation, so then the dimension makes sense coming from Murray von Neumann dimension. The map here, this map is injective because derivations are completely determined by where they send the generators. And this is closed just by argument of convergence that you can do.
Good question.
Yeah, go ahead.
Shouldn't the derivations be valued in just M tensor M op for it to be like this Leibniz rule over multiplying? Or like are we just viewing it in there for analysis purposes, even though the range lands in M tensor M op, or no?
So the derivation lands on here, and then I'm using the fact that this has a bimodule structure by M to define the Leibniz rule. Right? So thanks to the map that we have here, then we can just take a dimension by witnessing this as a subspace of our amplification here. And then you have to put the M here. I don't have space. Okay, so some subspaces that will appear as we move on. The first one is the inner derivations. This is the commutation relation. And then the other one that we're going to look at is given B a unital star subalgebra, we look at the derivations that vanishes on B. Is equal to 0. Okay, so everything right now is happening all at the level of A. So now we're going to start talking about the results. So one of the assumptions that I'm going to add on A is that it's going to be alpha invariant. So assume A is alpha invariant, which just means that alpha of G of A is a subset of A for all G. And then the polynomial algebra that I'm going to look at for the cross product is just taking A and then the, yeah, no, that's this way. The unitaries that we constructed before. And the alpha invariance, the reason why I want that is just so that any element in here, I guess we can call it A, is going to keep the following form that we had before, where it's going to be UG. Yeah, so I wanted to keep this. The other thing that we end up getting for free is that L2 of M cross product you can rewrite this as a direct sum of L2 of M tensor M up UG tensor UGH up. Okay, so these are going to play a big role. And the other thing that I want is these, I'm going to look at the projections associated to them. I'm going to call them PGs. PGH for the projections corresponding to this here. And the nice thing is that from looking at the Hilbert space, from looking at the subspace here, this is invariant under the von Neumann algebra of M tensor M up. So that just means that this commutes with those with the action coming from M tensor M up. So first result. There exists the following is a right M tensor M op module isomorphism. Okay, so the idea here is that if you give me a derivation at the level of the cross product so that the g's vanish, I can decompose it into derivations on A. And the way to do that is that what I do is I identify the L2 M tensor op module. So here one of the main tricks to also do is the following. So L2 of M tensor M op can be identified with L2 of M tensor M op UE tensor UE op. So this is how you restrict ourselves to the derivations. The one tensor H here is going to be a twist that I'll show you in a minute why it appears. So the first thing is if you give me a derivation on the cross product, so I don't want to write all of that down. If you give me a derivation here, what I'm going to do is I'm going to hit it by UE tensor UH op, restrict it to A. But now the thing is that I need it to land me back into E tensor M, and so what I do is I project down. And this is going to be a derivation on A tau. So that's how you restrict the derivation in the first place. Now to lift the derivation, the naive thing to do is because of the fact that you already know what it needs to do to the UGs, you just say, okay, you give me a derivation. Sorry? What do we know? Because it's vanishing. So, so you have a derivation. So the thing to do is just to do. So let's say the lift alpha of G x is going to be an A. So remember that the UGs tell you what the action does, so we can rewrite this as the derivation UG x UG star. And then we use the Leibniz rule to cut it, but the fact that it's vanishing in here, the only term that will survive, well, we can just do the computation completely. So this should be UG tensor 1, derivation x UG star plus derivation prime UG prime. Oh, no. This is going to be 1 tensor x. But this is equal to 0. And then here we break the derivation. We use the Leibniz rule again here. So this would be UG tensor 1, derivation x tensor 1 plus 1 tensor UG star. And then this term also dies because we're in the one that, because it vanishes at the UGs. And so the only term that then what ends up happening is the following: alpha g x is equal to UG tensor UG star. Right, but this is an extension, so because of the fact that the alpha g of x is living in A, you end up getting just this. And then on this one we do, well, it's the same. But the issue here is that with my identification, these terms just shift me out of the E tensor E off position. So the way to fix that issue is to average. So the extension, which I'm going to only show you for one, is the sum of G and just to double check. Okay. So inverse. Oh. Yes. Yeah. Because so this is what happens when you look at the E component. So this is when this is just E, and then the other one you're just going to hit it the same way that I hit it by one of these terms here to shift it to the other position. Okay. So this is what it does on A, and it's going to be 0 on the UGs that you can check.
Wait, but you've only told us what it is for x and A.
Yeah, but the derivation is completely determined by what it does to the generator.
So you're just formally defining it to be.
Yeah. But you can also check that this formula will kill it because pretty much, yeah, it's just an easy computation. Okay. So with a little bit more work, one more thing that I forgot to mention here is now that we have this nice formula, we can apply the dimension, and then the dimension, at least for as an M tensor MOP module, you end up getting the following. Because the action is trace preserving, this is not the shift that I do here is not going to affect it anymore. So that's why you get the order of G here. It's for free. And then this formula and a little bit more work gives us the following equation. Gives us this formula here. And then this is the Schreier's formula for at the level of the derivation. Okay? But now what we want to do is we want to bring this back to free probability, and the way to do that is it comes from the fact that a lot of other free probabilistic quantities are defined by subspaces of the space of derivations. And I'll give you a few of them now. Any questions so far? Yeah. Yeah, so if you give me a derivation at the level of the cross product, I'll do this procedure, and then I'll land you in here. DE is the component when this is one tensor, like when this is just the trivial one. So what you do to get the H one is you just hit it by UE tensor U op star. Okay, so in 2005, Connes and Shlyakhtenko defined delta A tau. This quantity comes from L2 cohomology. And then in 2009, Shlyakhtenko defined well, this one doesn't have a formal name, so it does capital delta here. So in here, I'm not using A because this one actually depends very highly of the generators. And then the other one that I have is so. Define the Freestyle dimension. So Charles and Nelson defined the Freestyle dimension. So this one actually has a name, which is nice. And this was done to approximate. So this one, I am going to actually give you the definition of where this derivation comes from. So this is equal to the dimension of the derivations 1 tensor 1, A tau. And then, 1 second. Should probably do this. Then the derivations. Okay, so these are the derivations for which 1 tensor 1 is in the domain of the adjoint. So what you would do is you would look at the maps that I defined, and you would make sure that this part here is preserved, and it's a little bit of work. These other two I won't define, but that was pretty much the idea. And then what I was able to obtain was the following theorem. I was able to get equality at each level. The new result that I was able to get through the help of peer review was to move this to the case when it's non-abelian. So that was nice. Okay. Okay, so now the last thing I'm going to talk about is the hierarchy that we have. So 1 second. Delta 0 of x is less than delta of x. Okay, so these last three comes from the paper due to Connes and Shlyakhtenko. This result is due to Guinto and Capitan, and also due to Jenny and David. And then this one was already known by Voiculescu. If you assume that M is non-invertible, then you further have the derivation this is a lower estimate for delta 0. So this is a mixture of like the non-microstates and microstate side, and then if you want something only at the level of microstates, we have the Friestein dimension. And you just copy the other one. Right? So the idea now is, given the results that we have from here, what we're able to do is that if these two terms are equal, which happens when they're both computable, what this formula tells you is that you can even lift it now to the level of a cross product by finite group. Similarly for this one as well. So if this one and this one in delta are equal, you get that as well. But this is what we have. Thank you very much.